Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends to the 14th lecture on design and development of wave energy converters of the course Marine Renewable Energy Systems, Analysis, Design and Development, offered by Department of Maritime Engineering at IIT Gandhinagar under the aegis of Swayam Prabha. Friends, we will continue to discuss the aspects of numerical analysis in frequency domain approach for primary design of wave energy converter. So, in the last lecture, we said that the heave degree of freedom is considered to be the more active degree of freedom for energy harvest. So, we modified the equation of motion to write that in the heave degree of freedom accounting for the relative motion between the central buoy and the floats. Then we also said that the hydrostatic force which is to be applied for the damping effect on the PTO is given by minus kh z hat omega, which is also equal to minus rho g a w z hat omega, equation number 1 for this lecture. Okay. Now, the external PTO force is induced as a linear damping force in the PTO, and this is applied in the heave motion to extract energy. Therefore, the coefficient of PTO is now represented as CPTO, which is as same as C33, where 3 is the degree of freedom in heave. Okay? And this will be a function of float velocity. Having said this, we can now write this velocity as real component of I omega z hat omega bar E I omega t. This will be in heave degree of freedom, which is given as, let us say, f hat PTO in heave motion will be given as minus I omega C PTO, that is the damping of PTO of z hat omega. Equation number 3, this is 2. Now, when the central buoy is connected to the mooring line, the mooring lines will always try to apply recentering force to the central buoy. Okay? Now, let us capture that. The recentering force applied to the central buoy which is indicated as Fm omega is generated by the tethers, is it not? And this will induce additional linear stiffness. Okay? So, that is captured as Km, which is given by or connected to Fm, is connected to the mooring line force as below. So, the mooring line force, which is the complex quantity, is connected to the stiffness of the mooring line like this. Equation number 4. Now, I substitute all these terms in the simplified equation of motion, which is now written as. So, what we did? We initially had equation of motion in 6 degrees of freedom. We simplified to 1 degree of freedom. In that equation of motion, there are many terms. We started understanding all these terms and we had these equations. I am going to now substitute this back to this equation to solve for this equation, right. I am going to do that to solve for this equation. I am going to substitute this back to solve for this. So, when you do that, I get the solution as z hat omega, because that is what I want, which will be the exciting force divided by minus omega square m plus added mass of omega, right? Plus stiffness of the moving line plus stiffness offered by the hydrostatic force plus I omega times of the radiation damping applied to the PTO plus the damping applied to the PTO separately. Okay, so this is my denominator, this is my numerator. The fraction of these or the ratio of these will give me the response quantity in heat degree. So therefore, the resultant power absorbed by the fluids which we call as the average power is what we are planning to extract by the device. How this is happening? This is or this happens by activating the linear PTO to the system, correct? And this can be expressed in watts per square meter, and this will be independent of wave amplitude, so which will be given as P average will be half C PTO omega square of Z omega square. So let us say this equation number 5, right? So this is 5, sorry, this is 5, cause equation number 6. Now I can always modify, by doing the following. I substitute because in equation 6 I have a term which is z hat. I already have in equation 5 z hat. So I am now going to substitute equation 5 in equation 6. So I now get the new equation as the average power absorbed by the PTO, which is given as the power average as half C PTO omega square F excitation energy or exciting force square then minus omega square mass plus added mass of the system plus moving stiffness, hydrostatic stiffness of the system minus omega square of C radiation damping plus the PTO damping square. Okay, PTO damping square. This is square term. Okay, so we call this equation number 7. Now, in this whole equation, we have one more factor which will govern the design. Let us see what is that factor. This is one more factor, an additional factor which will now govern the design is the absorption length, called as LB. What is the absorption length? This is defined as the ratio of average power absorbed by the device to the instant power offered by the wave. Some sort of an efficiency, but we are not multiplying with 100. Therefore, we simply say absorption length. Okay. So, LB is given by this equation. In literature, this is also called as capture width ratio. The device. Okay. Interestingly, this was introduced by Boudard and Falnes in the year 1975. So, now I write LB as P average H square by P of the radiated wave. Equation number 9, which is the capture width. We can simply say the capture width ratio. Okay. Now, this becomes the performance index of the device. So, if you want to compare different devices, we do not compare the efficiency of power generated. We compare them based upon the capture width ratio, not based on the efficiency, because efficiency includes the damping effect offered by the PTO design, the mechanical system of the PTO design, and the conversion mechanisms of the geometry of the converter. Whereas capture width ratio is a useful term to only check the geometric design of the device. It does not include any effect coming from the PTO design at all. Therefore, ideally speaking friends, one must use this ratio to compare the performance of different devices, because this will be a good indicator which will apply the logic only to the geometric design of the device proposed or developed. Okay. So, performance index of the device is referred to using capture width ratio, and we now agree that this will be independent of wave amplitude. And this is true if the formulation is linear. Therefore, friends, I now introduce a new term called capture width ratio, which is LB by L effective, and explain this with 100. So, we also call this as hydrodynamic absorption efficiency, okay, which is given by this equation 10. Now, what is L effective here? L effective is the effective length of the float. Look back the previous lectures, we already have the dimensions of the floats. We indicated what is L effective for a curved float, and this is actually equal to the extent of the wave front that the float encounters. Okay. It is not actually the geometric length of the float, it is the effective extent, the wave front the float encounters. Now, interestingly friends, if these floats are placed around the central buoy, as the floats are placed around the central buoy, the effective length of each float changes. Is it not? For our understanding, let us try to see how this effective length changes for different kinds of configuration. We already said the float, if it is flat, if it is open both the ends, the diameter is known as 0.6 and this value was 2.4, correct? You can also have your float with closed ends. You can also have a float with closed ends. So, you can also have a curved float with open ends. These are the configurations. You can also have a closed float with curved ends, bean shape. So, if you remember, this was identified as S1 configuration, S2 configuration, S3 and S4, okay, and so on. So, now we can always compare this with our position. We said that if we have a central buoy and if you want to place floats circumferentially that is one here and one here, another one here and another one here. This is our design and this becomes my wave incident angle. Okay. The farthest float was F1, is F2, F3 and F4 configuration and this is a central buoy. So, for this configuration, let us see what would be the effective length. So, let me write the effective length for 0 degree angle, let us see, okay, of the wave. So, one can see the effective length for this float F1 is taken as 2.4 for S1 configuration. Let us say we make this table for our understanding. Let us say the configuration, then the float nomenclature. We take the angle at 0 degree approach. So, configuration, let us say S1, S1 is a straight float, okay. So, I keep it here, let us say straight. So, I get this float F1 as 2.4. I will also get this for F3 as 2.4, is it not? F1 is this and F3 is this. As far as F2 and F4 are concerned, you will agree they will be only the diameter, okay. When I am going to place it this way, I get only the diameter as the effective front, right. So, only the diameter. When you look at, let us say for example, the S2 configuration. So, I would still say it is 2.4 for F1 and F3 and for F2 and F4 still 0.6 only, okay. When we talk about S3 configuration, the curved one, it is 2.4 for F1 and F2, sorry F3. For F2 and F4 it is going to be 0.84, that is the curvilinear projection of this. For example, if the float is placed this way, I am looking at this front, right. It is not simply the diameter, it is this front. So, it is 0.84, can be geometrically computed and so on. So, one can easily find out the influence of the configuration of floats and respect to the location in connection to the wave direction. One can find out L effective and that L effective is what we use in this equation here to compute the capture bit ratio. Okay. So, L effective can be computed geometrically from the calculations and so on. Now, friends, let us take this discussion forward. Let us see what are the design parameters of the floating wave energy converter, which is going to be looked into to harness the maximum energy. So, let us see, the first should be the shape, or let us say the geometry. I am talking only about the float, not the arrangement. The second could be the dimensions, the length and diameter. The third of course could be the water depth, because water depth has direct effect on the amplitude, and amplitude anyway imposes or decreases wave impact and energy on the system. So, now these factors or the above factors will influence the hydrodynamic coefficients, like for example, the radiation damping, the added mass effect, and the excitation force. Therefore, friends, when we talk about design of the floating wave energy converter, when we talk about the floating wave energy converter design, then it should account for the damping effects caused by the PTO, and the wave characteristics at the chosen site. So, they are site specific parameters, and of course, hydrodynamic coefficients of the design, which we saw in the last slide. So, all should be considered, and that becomes now an input for the numerical analysis. Maybe in the software, one can easily use ANSYS Aqua. There are other parallel softwares which can also be used as a tool for doing such analysis, but we are explaining this with a simple illustration using ANSYS Aqua. In this course, friends, you will also know the step-by-step screenshots of making a model and then doing analysis in ANSYS Aqua domain for solving such wave energy converter problems. So, for made in India concept applicable to Gujarat sea state, let us say for made in India concept, which is one of the vision of the blue economy of this country 2040. So, for the made in India concept, we will discuss two cases for my design. Apart from the geometric shape and size which has been optimized for a chosen geometry, the sea states, the location of installation also becomes a factor. So, we consider two cases, one the Arabian Sea, two the Bay of Bengal. So, these are the two predominant, let us say, the waterfronts, the sea front where such devices can be hosted. Okay. So, when you talk about this, we must understand the sea states. The sea state data is available in open domain or on request from NIO, National Institute of Oceanography, which will also give you the data of this. Let us say, to make an understanding of this, what are the typical annual mean wave periods. Annual typical mean wave period, which we call as T mean, they vary from 4 seconds to 10 seconds in these two sea states. And the significant wave height, friends, what are the wave period and significant wave height? We are not discussing those nomenclature in this course, but there are other courses where this can be easily learned, and I hope you will know them already. So, significant wave height, which is indicated as HS, is about 0.1 meter to 4 meters. This varies from shallow water depth to deep water depth. Okay. So, these are the typical values. So, the sources for this information can be seen from SO 2019. Of course, they are available in other sources as well. One can always do this to find out. Okay. So, therefore, friends, we gradually move on to the next stage of the design, where we are now going to do experimental studies to identify the influence of design parameters on the chosen geometry. Of the wick. Okay. So, for our study, we will simply say take the mean period as 5 seconds and the significant wave height as 2 meters. This is an example study. So, we stick on to this specific value and start scaling the wave parameters for the experimental studies to find out the efficiency of the chosen design. Okay. So, to do experimental studies, we need to have a scale ratio. Okay. So, we need to have a scale ratio to choose this. So, let us say we apply a model scale of 1:10. So, by applying Froude scale law, now we apply Froude scale law represent the wave characteristics for both Bay of Bengal and Arabian Sea. Let us say, for example, in Bay of Bengal, we choose to operate at shallow to intermediate waters, where we are going to install the device. We take the mean period as 5 seconds and significant wave height as 2 meters. Of course, this data is relevant to Bay of Bengal, as you see from this reference SO 2019. Okay. So, the scaled parameters must be chosen to look at the extreme values, so that I get the maximum power harnessed on the device during experimental study. Okay. Now, we also know, so it is a fact that the wave power or the absorbed wave power is directly proportional to wave height or wave amplitude. So, therefore, a maximum wave height chosen will give me the maximum power irrespective of diameter of the floats. But the most important thing is we need to choose the bandwidth of wave periods, because I am looking for the resonating condition of the design. So, we fix this operational range of this data less than about 2.5 seconds. So, what we consider here is beyond this range, WEC cannot operate. Let us say we fix this band. So, it is going to now operate within this range, and we are going to tune the WEC design to have the maximum frequency match with this application. So, I harness the maximum energy, okay. That we have to fix. If you do not fix this frequency band, you cannot design the system of WEC for resonating condition. You cannot design the system for a wide band where it will resonate for all bands of frequencies. I do not think it is a good design idea at all. Therefore, we have to fix that band, and accordingly we choose the dimensions of the WEC in such a manner that it comes closer to the near resonance frequency. Therefore, I can harvest the maximum energy in a scaled model during experiments as well as analytical studies. Okay, that is an approach we follow here. Okay. Now, then the question comes, what water depth we can do? What water depth we can choose? Now, we generally choose water depths of 5, 10 and 15 meters. The wave height is immaterial in the present case because the whole formulation is based on linear frequency domain. Throughout the investigation, the central buoy dimensions will be fixed. So, what we do here is we fix the dimensions of the central buoy. Okay. Only the float parameters are changed. In different ways. Of course, the wave approach angle varying from 0 to 45 degree is also a variable parameter for interest. Therefore, friends, for any given configuration, let us see what are the factors based on which the maximum power can be achieved. So, what are the factors which will govern the maximum power absorption? Now, remember, we are fixing the configuration. So, do not say that we have a geometric configuration also coming into play. We are fixing the configuration. For a fixed configuration, the response of the system depends on, but the response will govern the maximum energy, right, because I am talking about resonating condition. So, the response, we should say in fact the total response depends on 1 individual motion or the response of the central buoy and floats, individual, okay, and floats. 2, the influence of central buoy's response on the floats. So, there are 2 aspects here, and of course, vice versa. Okay, friends, let us look at this figure here. We have a central buoy, then we have floats equally spaced, symmetric about x and y axis. This is float 1, float 3, 2 and 4. This means instant wave direction. This is the central buoy. So, now we have different aspects that the motion of the central buoy and floats independently will govern the efficiency. 2. The influence of buoy on the float and float on the buoy will govern the efficiency. So, in our analysis, we need to cover both of them to understand in what way this can be maximum power generated. Okay. Furthermore, friends, one more important aspect is there, the interference between the floats can also govern. Okay. Between the floats, what would be the interference? This will also govern the power. Okay. Coming to the conclusion of this particular lecture, let us write down the summary of this lecture. The summary is, in this lecture we understood that how the equation of motion and the components are expressed in heave response. 2. We also understood something called capture width ratio. So, how it is important in the design and so on. So, please stay continued, friends. We will discuss this further in the coming lectures. Thank you very much. Namaste.